Dr. Samantha Wray is visiting us today from Dartmouth, where she's a research assistant professor and lecturer in the Department of Linguistics, with affiliations also in the Department of Psychology and Brain Sciences and the Cognitive Science program. Samantha's current work focuses on word recognition models for understudied language using behavioral and neuroimaging methods. Samantha received her PhD from the University of Arizona in 2016 and had a postdoc at NYU Abu Dhabi before her current position at Dartmouth. But most importantly, before all of that, Samantha was a student here at Western, where she majored in linguistics and English and also studied Arabic. So today's topic will focus on how psycholinguistic and neurolinguistic research can use manipulations of experiment design in combination with linguistic properties of understudied languages to expand our current models of language processing. So welcome back, Samantha.
Thank you. Okay, so today I'll be talking about how we can use different properties from across the world's languages to show us more about how the mind and brain process language. So this really great work here that is not any of mine, this is from a different lab, but this has shown that regardless of the language family or the specific language spoken, we can localize language to the left hemisphere and in these general kind of brain parts. So the same networks process language regardless of if you're speaking Armenian or Italian or what have you. Now this is mostly in the left hemisphere, especially for right-handed people. If you're left-handed, your mileage may vary. But it's been attested regardless of which language. Also, if you have a sign language, it's been attested for different neuroimaging methodologies and so on and so forth. But what research remains to be performed is what kinds of specific fine-grained information processing occurs where and on what timeline. So let me give you a concrete example that drives my research. Let's say you hear the word cat, or read the word cat, or see a sign for the word cat. Regardless of the modality, you're going to have to do some work here. So you'll have to activate the conception, like the concept of cat, right? So your conceptual frameworks have to be activated. This is going to activate some related words, maybe, dog or snake or other pets. And it's going to activate some phonology and phonologically related words, things that sound like cat, like mat or rat. Now, this whole enterprise is made even more complicated when we have a morphologically complex word like cats. So not only are you going to have to access cat and the things that sound like cat and the things that are semantically related to cat, you're also going to have to recognize that that "s" there is doing some work, right? It's a plural morpheme. And that's really important because if a friend asked you to look after their cat versus their cats, you're going to want to know how many cats you're in for. Otherwise, your house is going to look like this cat cafe down the street, Necco in Bellingham. So how do we do this? How do we take a complex word, break it down into its constituent morphemes, access those meanings, and then recombine it for the full holistic meanings? So here's the kind of pipeline I'm going to be talking about today. And there's many other stages we can look at along the way, but here's the three main ones I'm interested in. First, in this general area, you break down a complex word into its constituent parts. So here in yellow, you'll take something that could be a morpheme and from a word and break it off. Then you have to put those parts back together, and that's in blue and red. In red, you're going to check that these parts are morphosyntactically compatible, that there's the right part of speech for your particular morphemes. Then you're going to check that they're semantically compatible. So I'll walk you through these processes in detail in a moment. But I want to show how these models that we currently have for how we do these three operations, decomposition, and then the two stages of recomposition, morphosyntactic check and semantic check, are incomplete. So I'll show you data today from some research on Tagalog and also called Filipino. and Arabic, that's going to help elucidate how we do this a bit more. So the research from Tagalog is going to show us how infixes invite us to reinvent our models of decomposition. And the data from Arabic is going to show us how parts of speech have some psychosaliency, how they're considered psycholinguistically real in the mind. Now, there's something else at stake here I want to talk about, which is how does the brain work in general? So there's two major camps we could think of. One is that we're like a hard and fast rule checker. We're basically a calculator. When we are presented with information X, we have to do operation Y on it. When we're presented with information A, we have to do operation B on it, and so forth. So that's kind of like this. You're given information A, and if you're not allowed to perform a particular task on operation A, you're stopped. That's the hard and fast rule checking system. The other way that we can think of the brain as working is more like ChatGPT and other similar computational models. These kinds of things that are always in the news about artificial intelligence, in which, given a wealth of information, you're going to extract some sort of associative properties between them. So this is like a Pavlov's dogs type situation. This is not a hard and fast rule checker. It's, well, every time I happen to see information X, it happens to be associated with information Y, and that's why I do particular things. Anytime I see information X with some sort of new information it tends to not be paired with, then I get surprised, right? It's not that something stops me from processing it, but that there might be some sort of a response correlated with my surprisal. Now, ultimately, both of these are true, right? We have to process information in both ways. But many models of psycholinguistics and cognition in general are starting to become really enamored with the latter, with this ChatGPT type structure of our information processing, that everything is simply associative and we don't really have very many hard and fast rules in our mind. So today, this data I'm going to show you from Tagalog and from Arabic is not only going to come to bear on improving some of the psycholinguistic models we have, but also show us in which ways we're like the former, a calculator that's simply doing predetermined operations on information, and in what ways we're like the latter, ChatGPT, in which we're taking tons of information and building some associative statistical properties from it. So the data from Tagalog will show you that we're more like a statistical processor than previously thought. And the data from Arabic will show you that we're more like a hard and fast rule checker than previously thought. So again, both are true, but in different ways than psycholinguistic models have currently shown us. Oh, that clock is broken. I was like, how can I still be... I've been talking a while. Okay. All right. Let's take a look at this first study. So this is going to be the very first step of our pipeline. Taking a complex word and breaking it into potential constituent pieces. Now, this is done in an area of the brain called fusiform gyrus. And if we were to take the brain and tilt it on its side, that's what you'd see here. So here in red is the fusiform gyrus. And the fusiform gyrus is an excellent pattern matcher for things in the visual world. So I'm going to restrict this to the left hemisphere here. So you may have heard of something like propagagnosia. I knew it every time. Propagagnosia. Does anybody know how to say that? So face blindness. Easy. Face blindness is a dysfunction of this region, right? People who see faces regularly in the visual world can't seem to match them. Those of us who don't have face blindness are doing our face matching in fusiform gyrus. Those of you who played Pokemon as kids also have a Pokemon recognition area in fusiform gyrus. So these kinds of features that you had to train to pay attention to in order to distinguish different Pokemon from one another is also done in this region. purposes, though, we're interested in a part of fusiform that neither does faces nor Pokemon, but words. So the visual word form area, or VWFA, is also in fusiform gyrus. And just like matching Pokemon or faces, its job is to take this visual stimuli and match it to some representations we might already have. So it's doing the heavy lifting when you're seeing a word embedded in some sort of visual noise, or when you're having to distinguish words from just symbols or other things in your environment. Now, VWFA has been shown to follow some particular informational constraints. And this should hopefully get you thinking of hard and fast rule checkers here. So we know that given a particular word, you're going to break it down in VWFA into many, many parts. So something like farmer is processed here into its stem and affix, farm and But because this is a region that can also do some visual matching with things like Pokemon and faces and other things, it's not particularly smart. So a word like brother actually is decomposed into broth and in this region. But notice that both of these are potential stems and potential affixes. Broth is a word on its own. ER is an affix we've seen before. So a word like brothel is not automatically decomposed in this region because EL is not a potential affix. We've never seen that before. Similarly, winter is not automatically decomposed here because went is not a potential stem. Okay, we've never seen words with went. Now, we can go a little bit deeper into this and find out that also things that are suggestive of morphosyntactic role are automatically decomposed. So what do I mean by that? A word like excursion shouldn't be decomposed given the facts we have so far, but in fact it is. That's because it tends to appear in sentential contexts that other ION words appear in, which means that ION is affixy in this position. This is in spite of the fact that excursion is not a viable stem on its own. Contrast this with something like sausage. We don't see sausage in sentential contexts in which we see other AGE words, so that puts up a little bit of a block. We do not decompose sausage automatically. That would be extremely funny if somebody came in Zoom right when I was saying we don't decompose sausage. Now, all of this evidence for the facts that I've just laid out before you have been shown from various neuroimaging methodologies and so forth, but only for a small portion of the potential languages of the world and the potential language families. So with the exception of my own work in Arabic, which I'm not going to talk about today, but which exists, everything else is from a particular morphological kind. And we're aiming today to show a little bit more evidence in Tagalog. So what do I mean by a particular morphological kind? Well, what do these languages offer typologically with respect to morphology? If we look at the morphological types studied for all these languages, prefixation, suffixation, suffixation, prefixation. So we keep looking at these affixes over and over and over again. Suffixes, prefixes, suffixes, prefixes. So if we want to make sure that we are indeed a hard and fast rule checker, we're checking if something is morphosyntactically congruent, we're checking that there's a viable stem, we're checking that there's a viable affix, we need to look beyond just prefixes and suffixes to make sure. So here's where Tagalog comes in really nicely. Not only does Tagalog have things like circumfixes, in which you have a stem shoved in the middle of an affix, and reduplication, in which a stem repeats, we also have infixes, in which a stem is broken up and the affix is shoved right in the middle. So of course we don't have this productively in English, but we have it in freaking and related words like fan-freaking-tastic, right? You can break up the stem in order to infix something. Well, this is a normal morphological process in Tagalog. So it can make something like an adjective or past participle type. So note this word on the left here, sinubak. The stem here, oh, sorry, that says sintama twice. The stem here is actually sabak. The affix then is n. Now, sintama on the right is actually a morphologically simple word. So this is like winter. There is no stem, satoma. It's just a morphologically simple word, sintoma, and should not be decomposed. So let me talk about some of the methodology we used to look at this. When you are sitting with your brain in front of a computer screen, you can be given something like a stimulus. And that is intended to elicit particular responses from you. Now, the response can be something you give, something you do, right? Something that is like a button press. And that button press can be analyzed further with respect to reaction time, how quickly you're able to do something, and accuracy, how well you did something. So the behavioral data for this research is, I'm not going to talk about today because I think the brain data is more exciting, but I do recommend you take a look at the associated paper. But you're also doing something completely involuntary, right? You're pressing buttons, but also your brain is doing some thinking. So as we know, bundles of neurons fire together and that produces some electrical signal. But you may not be aware that all electricity has a magnetic field associated with it. So even this produces a magnetic field, your phone produces a magnetic field, and anything in your body that's making electricity makes a biomagnetic field. It's much, much weaker than all these electric objects, but it can be measured. So as your neurons are firing and this electricity is going, there's a magnetic field that's flowing out through your skull. And that response, as I said, is completely involuntary. You don't need to do anything in order for that to happen. You just need to be able to attend to a word like brother, and we can show, hey, your brain is decomposing this by analyzing the resulting magnetic field. We do that with magnetoencephalography, or MEG. So here's a picture of my colleague laying down with his head in this helmet that has 208 magnetic sensors around here. And that records changes in magnetic field. So if you're not aware of MEG, and I don't expect you to be, it's probably the least utilized neuroimaging methodology. It's great measuring time. So it can measure things on a millisecond by millisecond change, which is wonderful for studying language. A lot of the computations we do for language occur really, really quickly. But something like MRI takes, several seconds to measure blood flow. Blood is a really slow process. Electricity and magnetic field are really fast. So utilizing MEG, we can see how the signal changes millisecond by millisecond. It's just okay on space. So you don't get these beautiful images that you do with MRI. You instead have to do a lot of mathematical models to see where you think the signal came from. So some of the images today I'm going to show you might look more like potatoes than brains, and we're going to talk about regions in more general terms. Now, the magic that makes this whole thing happen is that there has been an established magnetic field change associated with decomposition in the visual word form area in fusiform gyrus. So it has to do with the relationship between frequencies of parts of words. So how frequent is the stem? How frequent is the entire word with the stem and the affix? And what is the relationship between those? What's the ratio? That ratio correlates really nicely with activity in fusiform gyrus. That's how we know a word is being broken down into its constituent morphemes. So the question we asked then with this Tagalog experiment is, will the activity in visual word form area correlate with this particular frequency measure? That's going to indicate a word was decomposed. So we have two options here, especially with respect to the fake infixes, like in syntoma, in which that's not really an infix at all. Just like winter, it just looks like one. Or just like in brother, it just looks like one. So either, yes, indeed, activity in visual word form area is going to correlate, which means we're more like Pavlov's dogs type, right? It's just, we're so used to seeing this infix over and over and over that we're going to automatically decompose it even when it doesn't result in a viable stem. If we don't see this correlation, we're going to interpret it in the following way, in which there's a hard and fast rule checker that says, hey, is this a viable stem? And if it isn't, then it won't have been decomposed. Okay, so at the Neuroscience of Language Lab in New York University, Abu Dhabi, we recruited 20 native speakers of Tagalog or Filipino, and they performed a visual lexical decision task. This is just to keep them active and entertained and attentive. So a visual lexical decision task is in which you are given a word on a screen, and you're simply asked, is this a real word or not? Okay. So we have lots of fake words mixed in there as well to keep people attentive and entertained. I keep saying that because your brain signals really do differ if you're attentive to something versus just kind of passively engaging with it. And also lying down in the MEG, which is a silent machine, and you're lying flat with a blanket, we do have a lot of people fall asleep. So this is what the brain data look like here. This is fusiform gyrus. So again, we've got the left hemisphere tilted on its side. It looks a bit more like a potato than a brain because we've inflated the brain. That's to get all the activity in the nooks and crannies and so forth. So what we're looking for is this component between, at about 170 milliseconds, that is where fusiform is going to be breaking things down. So here's the type of words we looked at, although I didn't have time to discuss reduplication, circumfixation today. I do want to show you reduplication is just two stems. Circumfixation is a stem with affixes on either end. And infixation is the affix shoved right in the middle. Remember also we have the fake infix, in which not really an infix, much like winter, doesn't really have a suffix. So we isolated this activity here, did a lot of corpus analysis to see the relationship between stems and words, what were the frequencies of these, and tried to see if there was a correlation. What we found is that indeed there was a correlation for reduplicated words. Yes, decomposed into two stems. No affixes necessary for decomposition. Circumfix words were also decomposed. Infix words also decomposed, great. But what's shocked us is that fake infixed words, like winter, were also decomposed. So even though stoma is not a potential viable stem in Tagalog, Tagalog readers automatically decompose this. So, is winter coming for stem viability? Perhaps. This shows us that we're more like ChatGPT than we want to be. Maybe. Maybe you want to be like ChatGPT. I don't know. No judgment. So, Tagalog allows us to see that when the stem is interrupted with an inserted affix, its viability is allowed. It doesn't matter that it doesn't result in a viable stem. There's still decomposition. This is something that we wouldn't have been able to study with English and would not have known. So we would have come to the conclusion, as we have been so far, with English and other related languages that have just prefixation, suffixation, prefixation, suffixation, that we're a hard and fast rule checker in visual word form area. In fact, we're more like a statistical likelihood checker. Let's move down the pipeline. So now we've broken words down, we have to put them back together. This results in two different stages, and these are localized to two different brain areas and two different time windows, and I'll show you that in a moment. The first stage of this is category licensing. That's making sure that the stem and its affix have compatible part of speech goals. The second part is computing the semantics of these combined morphemes. So let's take a look at this first part first. If we take the affix re, this prefix has some conditions to it, right? It has to attach with a verb. So repaint, reclose, rewrap are okay. Oops, sorry. Re-idea, re-napkin, re-sadness are not. And you might be able to kind of coerce meaning here. English is really, really good at making nouns verbs. And so you might say, oh, I need to refill the napkins of the napkin dispenser. I need to re-napkin the dispenser, right? But in general, re really wants a verb to attach to it. So this category licensing stage is going to make sure that the affix and the part of speech are compatible. The second stage, a combination, as I said, is computing the semantics. So re has to be attached with something that's not just a verb, but it's a verb that can be repeated and also completed. So we can repaint, reclose, rewrap again. Oop. But we can't re-smile, re-laugh, re-dance. Okay. So these are processes that are distinct in time and space, and we know this from previous MEG work on languages like English, Greek, and other languages that have heavy affixation. So if I perform a part of speech or category violation with something like re-idea, re-napkin, re-sadness, what happens is I see this activity elicited in this particular brain region, and again, it's just a potato because we've inflated it to see the activity inside the nooks and crannies, at about 200 to 300 milliseconds after you read the word. In a word with incompatible semantics between the stem and affix, we see in a slightly more anterior region an activity pattern that's a little bit later, so between 350 to 500 milliseconds. If you're reading something like repaint, you don't see either of these activity patterns. These are things associated with violations of those guidelines. So is it more like this, in which re wants to attach with idea but is stopped by a category check? Or is it that we tend to see re and paint and re and paint and re and paint, and so when we see re-idea, we get surprised, right? The former is a hard and fast rule. The latter is more like a tracking statistical properties. Now, here's the problem with all the research that's looked at this so far. Paint, idea, napkin, any of these already have a part of speech and category to check. They're free morphemes, right? They don't need any additional affixation to stand on their own. They can stand on their own as is. So in a concatenative morphology, in which you're simply taking a stem and putting affixes within it, you have something like reactivate, in which you have re, you've completely finished with that morpheme, then you go to active, you completely finish with that morpheme, and then you go to ate. It's like beads on a string, just one after another. We've already seen a slight variation of this with Tagalog, in which we have to insert an infix in the middle of a stem. But the stem, crucially, as I said, is free and already has a part of speech. Let's look at a more extreme example of infixation. So Arabic is a sort of your classic non-concatenative morphology, which means instead of beads on a string, you can concatenate one after another. It's more like the weaving together of morphemes. So here is a morpheme KTB. This cannot be pronounced. It cannot stand on its own, and it is not free like idea. But it has with it the semantics of writing. Now, no part of speech, so not writing as a verb, not writing as a noun, just writing. And it needs to be interleaved with these other morphemes in order to make words. So here, man are a noun place, yanu are a verb and he. So once you've interleaved those, then you get the words office or he writes. But neither the root nor the pattern, the former which contributes the semantic information, the latter which does some syntactical fine-tuning, neither of these can stand on their own. They have to be in a word, okay? So in contrast with words like idea, napkin, sad, or sadness, KTB is a bound morpheme. It can't stand on its own, and it has no category to check. So back to the world of MEG. Again, at New York University, Abu Dhabi, we had 18 native speakers of Arabic. And if you know anything about Arabic, it has great dialectal variety. So we had speakers of Egyptian, Palestinian, Lebanese, Sudanese, Tunisian, Libyan, and Moroccan. But they were all reading modern standard, the written form. Again, this was a visual lexical decision task, so no one slept. And here's the kinds of words they saw. So they saw some words that were totally fine, totally attested, found in any dictionary, found in any corpus. They also saw words that we categorized as a category violation. So here, the root, which is indicated in orange, has never been attested in a verb. So it's been attested in other types, things like nouns or adjectives, but never a verb. And that was our attempt at making a category violation with this bound morpheme. Semantic violation words here were formed by this root, has indeed been found in many verbs, but not this specific verbal pattern which indicates a passive reading. So the part of speech here would be fine. It is a verb, but it just can't have passive semantics. It's never been attested before. So here we have the predictions of this. If it's all about statistical likelihood, if this is a ChatGPT type, if it's just tracking the probabilities of what will happen, we're going to see the same results as we saw for English. We'll see that there is an activity pattern elicited by re-idea type words in which this root has never been attested in a verb and we've shoved it in there. And we'll see the same effects for semantic violation type, re-laugh, in which the semantics associated with that verbal pattern are not appropriate. If, however, it's a hard and fast rule, our results are going to diverge. We're not going to see category violation types because there was never a part of speech to check in the first place with that root. And in fact, that is what happens. Because the root has no part of speech to check, we do not see any activity elicited by category violation. So this means that part of speech or category does have some psycholinguistic reality. It isn't just a property emergent from lots of language. It might be that initially, as we're acquiring language, it is emergent, right? No one ever explicitly tells us this computer, that's a noun, this chair, that's a noun. But eventually we get enough language data that these rules emerge and solidify and become hard and fast. Okay, I'll be very, very brief with my conclusions, but I just want to underline that these understudied languages can teach us a lot about psycholinguistic models, as well as models of linguistics more generally. So the recognition of words may be more flexible than we previously thought. We had thought that this was more of a rule checker, that you're checking for stem viability and affix viability very early on, and that might not be the case. It could be that for languages which regularly break up their stems anyway, you're not going to have a stem viability constraint. Also, as I said, parts of speech do have some psychological reality. They're not just emergent from lots and lots of data, and properties of objects don't inherently result in us thinking about them as nouns necessarily. This is something that can be baked in as a hard and fast rule checker. So before I end, I just want to talk about this project called Savant that I'm part of. This is a very large international team that's constantly growing. And we're trying to sort of fill in some of the details throughout the map of the world's languages based on various properties of writing systems, morphology, syntax, and also the morphology-phonology interface. So there's currently research either in press or published for Arabic, Tagalog, Slovenian, Bosnio-Serbo-Croatian, and Bangla. And now we're expanding to look at more languages, including, strangely, no one's looked at Spanish before, Xhosa, and so forth. I'd like to wrap up by thanking my co-authors in this, as well as my funding sources. But most importantly, WWU, Linguistics, for igniting this spark of joy and this passion in my career. So it is because of Kristen Dunham's class that I took that I stopped being a serial major hopper and decided to be a linguistics major because I thought it was the coolest thing in the world, and I still do. So thanks to these people and others.